Are you going to introduce me or introduce yourself?
So yeah. So this is the fifth. So okay. So welcome to the fifth week of our higher category theory reading seminar. So today's speaker is Vaibhav from yeah. So yeah, he'll be talking about the last two sections of the second chapter of Cisinski.
All right. So
Vaibhav,
this one's
take
called.
it away.
Thanks. So this one is called model structures ex nihilo or nihilo. I don't know how to pronounce that, but if you look it up, it just means out of nothing. Although not really out of nothing, but basically, looking ahead, what we're trying to do really is going to try to construct a model structure on simplicial sets that, you know, we learned that model structures encode homotopy theories, and so this is going to encodes the homotopy theory of Kan complexes. Right. Obviously, later in the end, we want to construct a model structure that encodes homotopy theory of infinity categories, but this is the step you have to take before that, right? This is the simpler case. So this model structure is going to be called, he calls it Kan-Quillen, or some people just call it the Quillen model structure. And so, yeah, so in this chapter, he does things, as we talked about, in super generality about presheaves over some small category. So for us, just keep in mind that that small category should be the simplex category. Right. So let's recall from last time, this was 2.1.9. Let C be a locally small category with small colimits. Right. And let I be a small set of morphisms in C. And suppose there exists a cardinal kappa such that for any morphism in I, sorry, maybe I should put the functor out of K preserves kappa filtered colimits. So kappa filtered colimit, if you don't remember, is a, did I write it down? I didn't write it down. But it's like a colimit from a diagram that's kappa filtered so that every sub diagram of that diagram has a colimit that exists in C, right? A colimit, sorry, kappa filtered colimit. Yeah. Well, okay, you can look at that. I'm gonna try to remember it. So this just, I don't know if we talked about it, but this is sometimes called K is kappa small. If you're looking in, like, there's a book by Ulmer and somebody about locally presentable and accessible things, where they talk about stuff like that. Okay, so suppose all this stuff, and then the theorem says that then the pair so remember This means maps with the right lifting property with respect to I. And this means maps with left lifting property with respect to I. Right, so left lifting property against the right lifting. And this pair forms a weak factorization system, which you remember is one of the things that showed up in the definition of a model category. This is one thing, and then another thing is that and L of R of I is the smallest saturated class containing I. Right, so this thing was called the small object argument. And I don't remember if we saw this last time because I wasn't here, but okay, so this is one way of building a model structure on a category, right? Or recognizing a model structure, let's say. One way of on a category. And in the case that a model structure is determined in this way, when a model structure is in this way, we call C cofibrantly generated. Right, that is the set I of maps is a set of cofibrations. It's not all the cofibrations, but it's a set of cofibrations, and it generates in the sense that these things form your weak factorization system. So this guy left lifting against right lifting against I is your cofibrations, and this guy, in this case, this guy is your cofibrations, and this guy is your acyclic fibrations. So in this section, we want to construct such model structures on categories of presheaves. Or over small categories, or A is a small category. A is small. Okay, so this process for Kan complexes was constructed in a book by Gabriel and Zisman, or Zisman. I think it's called Homotopy Theory of Simplicial Complexes or something like that. I'll put the full title on the website later. And as we said, Cisinski does this in super generality over just arbitrary presheaves, which is useful later on when we do base change things. We'll see that. But just to keep that in mind, that to keep yourself on the ground, that we're going to do this for simplicial sets, right? So our category is going to be the simplex category, and category presheaves is simplicial sets. All right, let me pause there, see if there are any questions or comments. All right. So for the well, let me move on to the page. For the rest of this, let A be a small category, as we talked about. A hat be presheaves of sets over A. And this is not in the book, but I'm just going to write this for myself. I'm going to say mono A is the collection of monomorphisms. Monomorphisms in this category. So first thing he defines is a cellular model, which is a small set M of monomorphisms in A such that L of R of M is the entire collection of monomorphisms. Okay. So for example, when A is a simplex category, or more generally Eilenberg-Zilber category, then the boundary inclusions form a cellular model. A cylinder of a presheaf X in A is a commutative diagram of this form. This is going to look like the diagram that shows up when we define cylinders in model categories. Right. So we have this guy of our codiagonal, and we're going to call this, he calls it I of X, and we're going to see why he calls it this, but you can call it cylinder of X if you want. And so it's a commutative diagram of this, where this guy is the cylinder object. Such that the map, this map, delta 0, delta 1, is a monomorphism. A functorial cylinder. Okay, so maybe I should have mentioned this earlier. This entire section leads up to one theorem, that is theorem, I think it's 2.4.19, which is the construction of such a model category. And to unpack that instruction, or to unpack that theorem, these are all the definitions that show up in there. So this is what we're going to do. And then the last half of the section is proving that theorem, which gets very intense, which I don't think I have time to get into, and I didn't fully read anyway. So yeah. So a functorial cylinder is a functor I from a hat to itself, along with a natural transformation called D0, D1 from this guy to I, and a morphism that he calls sigma from I into identity A hat, such that for any X for any presheaf X, the diagram, similar diagram as above, Oh, sorry, the diagram. So there's a tensor product showing up here. I'll talk about what that is, but I just want to write down the diagram. Okay. Let's talk about what this tensor product is. Here the it's an action of this endomorphism category onto the category of presheaves itself. So it looks like this. I think he calls it end. That takes a functor I and a presheaf X, and it sends it to tensor X, which is just I of X. Okay, so let's say C 2.4.7. Oops. All right, let me pause there. Okay, and then an exact cylinder is a functorial cylinder satisfying the following two things. Functorial cylinder I commutes with small colimits and preserves monomorphisms. And I'm going to do this on another page. For all monomorphisms, of presheaves, the diagram. ID, J. So this diagram is a pullback diagram for epsilon equals 0 and 1. Okay, so let this be the sub-object. So sub-object is an isomorphism class of monomorphisms into I, determined by the monomorphism for epsilon equals 0, 1. We call the boundary of I the union of these guys. Goes inside of I, or has a monomorphism going to I. And this is, again, in, should remind you of how cylinders should act, right? In like a typical cylinder, where the cylinder object in topological spaces, if you want to be really concrete, or concrete, like the unit interval, right? So these are the two ends of that interval. And we can form for any monomorphism and inclusion right. So this, he describes this more explicitly in, let me write down what the remark is, 2.4.9. And we'll start to see such things show up a lot in homotopical algebra if you haven't seen these already. Like these kind of look like push out products type things. Okay, and then that was just a remark. Let I be an exact cylinder. And AN a collection of morphisms of presheaves. AN is called class of I-anodine extensions. If it satisfies the following. There exists a small set of monomorphisms such that AN is this way. Left lifting of right lifting of lambda. AN1 for all monomorphisms. And A map sorry, this map is in this class. Yeah, 2 for all maps. This map is an AN, again, for epsilon equals 0, 1. Wait, there's no epsilon. Maybe. I wrote something down and then it's wrong. There's no epsilon. Okay, all this, and then another definition. A homotopical structure. Topical structure is a pair I, comma, an, where I is an exact cylinder and an is a class of I anodyne extensions. Okay. So you guys have to remind me to move this up. I can't see.
Yeah.
And okay, so such a thing. I think exact cylinders will always exist. One can find such a thing, given assuming some assumptions. And so an example of extensions is all, if you collect all monomorphisms in some presheaf category, then this is I anodyne. And another thing he does is, given, I won't go into this, but given an exact cylinder I and some small set of monomorphisms, he describes a process of I'm running out of space. One can construct the smallest class of I anodyne extensions containing S. 2.4.13 describes this. All right, let me pause there. So now for this next part, I'm gonna think. So say for this section, say we have a homotopical structure fixed, call it IAN. Okay. So you have two maps, F0 and F1. A, then an I homotopy from F0 to F1 is a map. Like this with what you expect, H of the one side of this guy. Yeah, should be F0 and H of the other side. Right, and we can form a category. He doesn't call it this, but I'm just going to call it this, which is presheaves of A over A up to I homotopy, basically. So objects are objects of presheaves over A, and then we'll call it bracket. It's just up to I homotopy. you have to show that this is a equivalence relation first, and so on, but it describes that in the book. The rest of my notes, I think I wrote somewhere else in my notebook. Okay, yeah. So we're getting close to the main theorem. So hang in there. So following our equivalent, a map is an oops. Yeah. So let's say a map in presheaves is an I homotopy equivalence if it's an isomorphism in this category of two I homotopy equivalents. Okay, so a map is an I homotopy equivalence. There exists a map going the other way, which behaves as you would expect with GF is I homotopy equivalent to identity, and FG is I homotopic to identity on Y. Pushing forward gives a bijection, and pulling back gives a bijection. Y. A strong deformation retract is a map such that there exists a map G going backwards, such that there exists a map G and there exists a map H, and this guy such that composing these gives you the identity. H of this guy gives you identity on Y. H of the other side gives you FG. So this is a homotopy from FG into the identity of Y. This composing one way gives you just strictly equals to the identity of X, and the other way is just homotopic, and then H of this guy is sigma of F, where sigma was that is this identity of A into a natural transformation. So let's say recall a trivial fibration is a map that has the right lifting property with respect to monomorphisms. And proposition, any trivial fibration is missed. So strong deformation retract, and then I forgot to include, there's another thing called dual of a strong deformation retract, respectively, if and the morphism K of this boundary everything's just, you know, the dual is of what you'd expect. So K of the other side equals GF. And last one is FK equals so trivial, any trivial fibration is the dual of a ink strong deformation retract. And any section of a trivial fibration is a strong deformation retract. And any trivial fibration has a section and is an I homotopy equivalence. Okay, now we are very close because we can start defining what the fibrations, cofibrations, and so on are going to be in our model category, right? So what he calls as a naive vibration. Is a map which has the right lifting property with respect to these I anodyne extensions. So if this is an I anodyne extension, then there exists a lift like that. And say X, the presheaf, is a fibrant object. If the map into the final presheaf, which I'm just going to call star, is a naive vibration, as we would expect. A cofibration presheaves. This should be of presheaves as well. Is a monomorphism and a weak equivalence is a map such that for any fibrant pushing forward, pulling back, is a bijection. All right, let me pause there for a minute, because that was a lot of stuff. So this is the main point of what we were trying to do with all this definitions and stuff like this. So the theorem is that the above defines a cofibrantly generated model structure on a het. Further, a presheaf is fibrant in the model category, right? In the sense if this map is of naive vibration. And this model structure, if and only if the map to the final presheaf is a naive vibration. That's above. And a morphism between fibrant objects is a fibration if and only if it's is a fibration, again, a vibration in the model structure if and only if it's a naive vibration as above. Okay, so for us, we're going to use this to, I think in chapter 3, we're going to use this to describe Kan-Quillen model structure on simplicial sets. In which vibrant objects are precisely Kan complexes. This is what I mean by, this is what I meant by encodes the homotopy theory of Kan complexes, right? Those are your vibrant objects. And vibrations are Kan vibrations. So if you don't remember what these are things that lift against all foreign inclusions. So, all right, I'll pause there because this is the whole point of this whole section, basically. The rest of this is just proving this, which we only have 10 minutes left, so I'm not going to go into that. But also, as I said, I didn't read it. Any comments or questions on that? All right, real quickly, let's see what the last section is about. It's kind of technical. It's just some definitions that might come in handy later, but let's just describe them so we see what they are. So we're not blindsided later. This is called absolute weak equivalences. So here, let A be a small category. Presheaves over A. I, an exact cylinder. And AN of anodyne extensions. And the presheaf S. Okay. So 2.5.1 is the remark. There's an equivalence. So this looks silly, but this is presheaves over A slash S, which remember from I think chapter 1 is like the category of elements. Right, and those are generated by kind of things that look like this, representables over S. And then this guy is the over category. The presheaves over S. So it's just like presheaves over S. This is what morphisms look like here. This is what morphisms look like here. Now, given an exact cylinder and a class of anodyne extensions over a hat, we can define such things over this guy. So we can define I sub S, an exact cylinder. S and a NS, class of I sub S anodyne extensions. The morphism in this guy is an S equivalence if and only, or sorry, if it's a weak equivalence in the, so this defines a, remember this pair defines a homotopical structure, and we can use that to define a model structure, and the model structure determined by this pair. And a morphism in, is an absolute equivalence if it's an S weak equivalence for any S. And any map. Okay, so this will show up, I think, when we do base change things, because these are kind of looking at presheaves over some fixed presheaf, or varying that presheaf and seeing what happens. Okay, and then I guess the last thing is there's a proposition that says a monomorphism F is an this class if and only if F is an absolute weak equivalence. And a map G in that is a naive vibration in this model, in this structure, and an absolute weak equivalence if and only if G is a trivial vibration. Okay, and that's more or less all of it. Now, yeah. Any questions, comments?
So let us thank Rahul.
Sorry, I know that's a lot. No, homotopical algebra is not so fun getting into the weeds of it.
Yeah, I wanted to ask, I mean, did you mention that, I mean, maybe I missed it, that the push out product of tomorrow, I mean, so the push out product, the push out product of anodyne extensions is like also anodyne. I mean, just, I mean, did you mention that?
No, I didn't mention it, but I think
yeah, that's maybe a comment, and if you didn't mention it, we can show that push out product. Little,
yeah,
nice.
Yeah, I would say don't worry if this stuff doesn't stick immediately, but just you've seen it now, and so once you see it later in the proofs later on, you'll know where to look.
Yeah.
And look through the proof of that theorem, because it's crazy. Kind of.
Maybe you can stop the recording.
It will stop the recording.